In this video, we're going to be taking a look at two lens problems and two curved mirror problems. A lot of times these problems are referred to the use of the thin lens equation. So we have two formulas, one up top over here on the left and one over here on the right. Now for number one, it says an object is 1.85 centimeters away from a converging lens that has a focus of 2 centimeters. What is the distance of the image and what is the height of the image? The first thing I like to do is I like to do a sketch of the ray diagram. That way I can get a rough idea of what I want my solutions to look like. All right, so now that I did a quick sketch of the ray diagram, I sent one ray of light into the lens and then bent it through the focal point, or just kind of roughly made up, and then one right through the middle of the lens. Because those two rays didn't intersect with each other, I had to dot them back and then create a virtual image. So I have something that is on the virtual side, and it's upright, and then the height of it is taller. So I want to make sure that when I get my answers later, those numerical solutions match up with the image that I created for this ray diagram. So let's go ahead and start plugging in our numbers. We're going to start off with this formula over here because we have our distance of the object and our focus. So then we were going to want the distance of the image first. So 1 over di plus 1 over 1.85 equals 1 over 2. Now my unit is normally, the standard unit for distance is normally in meters, but I have everything in centimeters. So as long as I stay consistent with that unit, my answer is going to come out in that unit as well. So my distance of the image is just naturally going to come out in centimeters. So I can go ahead and subtract this number, 1 over 1.85, from both sides. And then I would get 1 over di equals negative 0.0405. And then what I'm going to do is I'm going to finish off by cross multiplying those two. And then my distance of the image is 1 divided by negative 0.0405, which comes out to be negative 24.67. Now I got a number for the distance of my image that is larger in magnitude than my distance of the object and is also negative. That does hold up with what my picture looks like here. I'm on the virtual side. The same side of the object with a lens diagram means that it's virtual, so it should naturally come out negative. And it does look like it's farther away from the actual lens. So this 24.67 should be considerably larger than this 1.85 as far as its magnitude of distance from the lens. Now, secondly, I want to find the height of the image. So I'm going to have to go to this formula over here. So normally you're using two ratios, and the height of the image is my HI. The height of the object is 2 centimeters, as given in the problem over here, equals negative DI over DO, the distance of the object. So then basically all I'm going to do is these two negatives are going to cancel each other out. So I'm going to divide these two numbers and then multiply both sides by 2. And then after I do that, I got my height of the image, which comes out to 26.68 centimeters. Now I want that number to be positive and larger than the 2 centimeters. This black arrow here, which is the representation of my image, is much larger than the original 2 centimeters and is positive to show that it's an upright image as opposed to an inverted image. So both of those check out. Those two answers look pretty good. So let me go to number 2. For our second problem, we have a diverging lens that has an object 100 centimeters away from it and produces an image 20 centimeters away from the lens on the same side. What is the focal length? So I'm going to go ahead and sketch that ray diagram first before we get started. All right, so drawing the ray diagram, having an object that's outside the focus is going to produce an image that's around here, and it says that it's 20 centimeters away from the lens on the same side, so that looks like it's about right. It's much closer to the lens, and it's on the same side. So if I'm looking for the focus, I'm definitely going to use this formula over here because that is the only one with an F in it. So I have my distance of my image, and then plus my distance of the object equals 1 over the focus. Now, because my image is on the virtual side, it's on the same side of the object. Anytime you're on the same side of an object for a lens, that's considered the virtual side. So this is going to be negative 20. So if I go ahead and take 1 over negative 20, I can go ahead and do this by hand. We have negative 5 over 100 plus 1 over 100. So that's going to give me negative 4 over 100 equals 1 over f. And then I can go ahead and do a little cross multiplication here. And then the 100 is going to flip over here, divided by negative 4. 100 divided by negative 4 is negative 25 centimeters. And that does check out. Your focal length for a diverging lens should always come out to be negative because a diverging lens doesn't actually have any light rays physically converging. So your focal length is always going to be negative, and that does check out. And that focal length is outside of that 20 centimeters, which it should always be a little bit outside the image of the object. So that does also check out as well. So that negative 25 centimeters looks good. Now for our mirror problems, we have a concave mirror that has a center of curvature of 6 centimeters. If 1.5 centimeter object is 12 centimeters in front of it, what is the distance of the image and what is the height of the image? So let's go ahead and do our ray diagram first. All right, so I created a ray diagram and I have an image that is closer than the distance of the object. It's inverted, and this time it's on the real side because we're talking about a mirror. So the real side is on the same side of the object because that's where the light is actually converging. So if I go ahead and use my first formula, this one over here, we have 1 over the distance of the image plus 1 over the distance of the object equals 1 over the focal length. Okay, the focus is actually 3 centimeters because it says the center of curvature of the lens is 6 centimeters, and the center of curvature is always double of what the focal length is. So let's go ahead and work this out and solve for the distance of the image. All right, so what I did is I subtracted 1/12 from both sides. I made the lowest common denominator of 12, so 1/3 minus 1/12, I changed that to 4/12. After I subtracted them, I got 3 over 12, and then I cross multiplied them, so the 12 popped up and over to the numerator here, and the 3 dropped below it. 12 divided by 3 is 4 centimeters for the distance of the image. So that is a number that is smaller than the distance of the object, which is 12, and it is positive because it is on the real side, so that does check out. Secondly, I'm going to go ahead and find the distance, the height of the image. So I'm going to go ahead and use this formula over here, the one for with the 2 ratios and the magnification, and I'm looking for the height of the image. We know the height of the object is 1.5. And then we now know the distance of the image is 4, and then the distance of the object has always been 12. So if I just multiply both sides by 1.5, then I have my answer, which is negative 1/3 times 1.5. So my height of my image is negative 0.5 centimeters. So that should be smaller than my original height, and it should also be negative to show that it's inverted. So my little orange image over here is inverted, and does also look a little bit smaller than my distance, or excuse me, the height of my object. Although my drawing's not great, the orange arrow is a little bit smaller, so it does look like it does match up with my numerical answer in purple over here. All right, so let's go ahead and take a look at our final problem. It says an object is 100 centimeters from a convex mirror. If the focal length is 6 centimeters, then what is the magnification? This is supposed to say then. So for the magnification, as long as we have either the height of the image and height of the object, or the distance of the image and distance of the object, then we'll be good with finding the magnification. So as of now, we have 100 centimeters from the convex mirror. So let's go ahead and sketch that diagram. Now with a convex mirror, we're always going to go straight, line it up through the focus in the back here, and then angle that out, and then go towards the focus, hit the mirror, and then reflect it back straight. So we have distance of the image, which appears to be less than this distance over here. The distance of the object seems to be upright, and definitely the height is a lot smaller. So based on what I have here, I'm going to go with this formula over here now, 1 over di plus 1 over do equals 1 over f. And I have 1 over and then negative 6, because if you have a focal length for a mirror or lens where the light isn't actually converging, you want to make sure that's negative. So we have that with a diverging lens, and we have that with a diverging or convex mirror as well. And then we're going to go ahead and then set that equal to 1 over 100, distance of the object, plus 1 over distance of the image. Okay. Again, what I'm going to do is I'm going to subtract 1 over 100 from both sides, and that's going to give me negative 0.176 repeating on that side, and then I'll have my 1 over di on this side. So if I go ahead and cross multiply these two, my distance of the image is going to be negative 5.66 centimeters, because it's on the virtual side and it does look like it's closer to the mirror. So that does match up with what my drawing looks like. Now, that wasn't my main goal because I want the magnification. I want to use that di to make that ratio over here, and then I'll have my magnification. So negative di over do, and then my magnification comes out to 0.057, okay, which is unitless, because if you are dividing something in centimeters divided by another thing that's in centimeters, the units are going to cancel out. And the magnification is fairly small because anytime you see an image with a convex mirror, it's always going to end up being smaller. So your magnification should for sure be smaller than 1. That checks out. So I hope that was helpful in helping you work out and understand thin lens equations with some different lens problems and mirror problems. Thank you for watching and listening.